Welcome back to part 2 of solving systems of equations in 3 variables. Let's go ahead and take a look at our 2 additional examples. Again, the first thing we want to do is label each equation. So we'll call this equation A, this equation B, and this equation C. We need to choose 2 equations and eliminate one of the variables. And it doesn't matter which variable we eliminate first, but let's go ahead and eliminate the x variable from the first 2 equations. So if this is a positive 4x, we want this to be a negative 4x. So we're going to multiply equation B by negative 4 and then add it to equation A. So we have negative 4 times B and then add it to equation A. So negative 4 times equation B will give us negative 4x. Negative 4 times negative 3y will be plus 12y. Negative 4 times 2z will be negative 8z or minus 8z equals negative 8 times negative 4 is positive 32. We're leaving equation A the same, so we have 4x plus y plus z equals 17. Let's go ahead and add these 2 equations together. The x terms are eliminated. We have 13y minus 7z equals 49. Now we have to choose 2 different equations and eliminate x again. Let's work with equation B and equation C. So if this is positive 5x, we now want this to be a negative 5x. So we'll multiply equation B by negative 5 and then add it to equation C. So again, we have negative 5 times equation B plus equation C. So multiplying equation B by negative 5, we're going to have negative 5x plus 15y minus 10z equals negative 5 times negative 8 will be positive 40. Leaving equation C the same, we have 5x minus 2y plus 3z equals 5. We'll add these 2 equations together. The x terms are eliminated. We have 13y minus 7z equals 45. So these 2 equations with 2 unknowns we'll call equation D and equation E. And we need to solve these 2 equations as if they were a system of 2 equations with 2 unknowns. So let's go ahead and eliminate the y term. So we're going to multiply equation D by negative 1 and then add it to equation E. So multiplying equation D by negative 1 is just going to change all of these signs. So we'll have negative 13y plus 7z equals negative 49. Equation E stays the same. Let's go ahead and add these together. And we'll notice that the y terms and the x terms are eliminated. So we have 0 equals negative 4. Well, of course, that's not true. This is an indication that there's no solution to this system. Let's go ahead and take a look at this system graphically. Here's the graph of the 3 planes. And what we'll notice is there are no points that are on all 3 planes at the same time. If you take a look at it from this angle, we can see each pair of planes intersect, but there's no points where all 3 planes intersect at the same time. Therefore, we have no solution. Let's go ahead and take a look at one more example. Again, we'll start by labeling these equations. Just for a change, let's go ahead and eliminate the y terms this time. So if we look at equation A and equation B, notice the y terms are already opposite signs. We want this to be minus 2y, so we'll multiply equation A by 2 and then add it to equation B. So we'll have 2x minus 2y plus 2z equals 8, and equation B remains the same. 5x plus 2y minus 3z equals 2. Go ahead and add these together. We have 7x, y terms are opposites, minus z equals 10. And we'll call this equation D. Now we'll select two different equations and eliminate y again. So if we work with equation A and equation C, if this is plus 3y, we want this to be minus 3y. So we'll multiply equation A by 3 and add it to equation C. So we'll have 3x minus 3y plus 3z equals 12. And equation C stays the same, 4x plus 3y minus 4z equals negative 2. Adding these together, we have 7x, 0, minus z equals 10. We'll call this equation E. Now we're going to solve the system using equation D and equation E. One thing we'll notice right away, though, is these two equations are identical. So if we were to try to eliminate either x or z, they'll both be eliminated. Let's go ahead and try it anyway. Let's multiply equation D by negative 1 and then add it to equation E. So we'd have negative 7x plus z equals negative 10. And then we have 7x minus z equals 10. If we add these equations together, notice that everything's eliminated. So we end up with 0 equals 0, which is true. This is an indication that there are an infinite number of solutions. So what we'll do now is express the relationship among x, y, and z to show there's an infinite number of solutions. So to start off, what we can do is take one of the equations with two variables, let's say equation E, and we'll solve this for z. So if we add z to both sides, we'd have 7x equals 10 plus z. Subtracting 10 on both sides, we have z equals 7x minus 10. So our solution could be expressed in this way. If we let x be any real number, then the z-coordinate must be 7x minus 10. Now what we'll do is go back and express y in terms of x. And the way we'll do that is we'll go back up to one of the original equations, let's say equation A, and solve it for y using x for the variable x and 7x minus 10 for z. So using equation A, we would have x minus y plus, instead of z, we'll use 7x minus 10 equals 4. So we'll solve this for y so that we have y in terms of x. So x plus 7x would be 8x minus 10. Let's go ahead and move the y to the other side, so we'll have equals positive y plus 4. And if we subtract 4 on both sides, we'll have y equals 8x minus 14. Now this solution is expressed in terms of x. It could also be expressed in terms of y or z, and it would look different, but the relationship would be the same. So what this tells us is we can find one of the infinite number of solutions to this system by selecting any value for x and then using these rules to find the y and z coordinates. Let's go ahead and take a look at this graphically as well. These three planes intersect in a line, as we see here in red, and the ordered triple that we showed on the previous screen would represent any point on this intersection, which is this red line. Okay, that's going to do it for this video. Thank you for watching.